So this video is about section 9.1, which is our first section in chapter 9. And we're going to be talking about differential equations for the next few weeks. And a differential equation, often referred to as a DE, so you'll often hear me say DE instead of differential equation. That's our abbreviation for these things. It's just any equation that contains both an unknown function and some of its derivatives. And I guess at least one or more of its derivatives. So we're talking about some kind of equation. Equation will have an equal sign in it. It'll have a function, some unknown function. Usually we talk about y, and also one or more of its derivatives. So maybe y prime, maybe y double prime, and in some kind of combination. So some examples, these are really real world applicable. So if you like the real world stuff, this next chapter is going to be really interesting for sure, because we have a lot of applications of these things. So in particular, you might see something like dp dt. So this is a derivative is equal to k times p, where p is the same p here, and k is a constant. And this is an example of population models. So you'll see a lot of things here related to population will look something like this. And so it's sort of that the rate of growth. So the growth rate, which is this guy, right, is proportional to the population size. So the proportion is the constant to the actual population size. So a population model we'll see a lot. We'll also see things like dp dt equals kp times 1 minus p over k. And this is what's known as the logistic equation. And it models sort of world growth or world population growth. And we're going to see these equations again later, but I'm just trying to give you some examples of what a differential equation might look like. And one other one, if you're interested in physics, that you may have seen before is m d squared x over dx squared, or dt squared, sorry, is equal to negative kx. And that's the motion of an object with a mass m, so m stands for mass, at the end of a vertical spring. So this is a motion of an object with mass m at the end of a vertical spring. So those are some examples of differential equations that are actually have like real world applications. Population models, logistic equation, and sort of springs that are moving in a certain way. So this video is really going to get us into a lot of the language of differential equations that we'll be using throughout the chapter. So the first one we'll talk about is the order of a differential equation, and that's the order of the highest derivative. So what you're talking about when you're talking about order is you're looking for the highest derivative that occurs in the equation. And so, for example, in these first two examples up here, these are first order differential equations because the highest derivative is 1. Whereas the mass example, this example here, this example is a second order differential equation. So we have first order if it only has first derivatives, second order if the highest thing is of order 2. So that's order. The next thing we can talk about as a differential equation is called linear. If we can write it in the form of like a constant, some kind of function of x times y to the n, like the nth derivative, plus another an minus y. There should also be an of x there, so it's missing that. Y to n minus 1th derivative of y, and keep going down until we have some function of x times y prime plus some function of x times y equals some other function of x. So if we can get a linear equation, a linear differential equation is just a linear combination in terms of x's of powers of derivatives. So we're going to look at some examples to talk about both whether it's linear or not, and if we can give the order. So here it looks like we have 5 examples. We're going to go through and talk about if it's linear or nonlinear, and then we're also going to talk about the order. So we'll do linear or nonlinear, and then we'll also talk about the order of each of these. So here on letter A, we have y prime is equal to 3x squared. And in this case, it is in fact linear because there are no, the derivative is just y prime. So that's great. And the order here is 1 because the highest derivative is 1. In this next example here, if we look at this guy, it is not linear because this term right here is a cubic of a derivative. So this is nonlinear with respect to derivatives. So it's a nonlinear differential equation of order 2 because the highest derivative order is of to the second power. The next one that we'll look at here is the second derivative of y with respect to x plus y is equal to e to the x. This is in fact linear because it is just derivatives. There are no powers of derivatives. This is just a plain second derivative. That's actually the only derivative that appears, so that's linear in its order, and we also have just a plain y. And if we look at the order here, this is an order 2 differential equation. The next one we see here is y double prime minus y triple prime minus y double prime plus y prime minus y equals t. And again, that's linear. There's no strange things happening with the derivatives. The derivatives are not raised to exponents or anything like that. We just have straight derivatives. And if we look at this, the order of this guy is going to be 3 because that is the largest derivative that we take in terms of order. And the very last one, if we look at this, dy dt equals t to the negative t times y minus 1. And again, that is also going to be linear because in terms of y, right, there are just a dy dt and a regular y. There's no sort of strange things happening with y in terms of exponents or other functions. And then the order of this one, if we look, it looks like the only derivative I see is the dy dt, which is of order 1. So you should be able to kind of talk about differential equations as whether linear or nonlinear and what kind of order you might see for a differential equation. The next words that we're going to talk about or use, we'll say a function is called a solution to a differential equation if the equation is satisfied when y equals f of x and its derivatives are plugged in to the equation that we have. So if we take a function y equals f of x and if we plug that in and it ends up working, then that is something that is known as a solution. And then sometimes we require that solution to satisfy a particular condition, like maybe y of some number is equal to some other number, y0. We call this condition an initial condition. So you'll hear me use that phrase a lot, like, oh, we're looking at an initial condition. And the problem of finding such a solution to this kind of differential equation is called an initial value problem. And we'll see a lot of these as well, so you want to just make sure you're familiar with that terminology again, and that's what's known as an IVP, an initial value problem. Okay, so that's kind of the situation. We have linear, nonlinear, we have order, we're going to be talking about solutions, we're going to be talking about initial values, and we're going to be talking about initial value problems or IVPs. So those are kind of the language that you want to get used to as we start looking at differential equation questions. We're going to work one example here in this video, and then in class we're going to focus on talking about what a separable differential equation is and how to work differential equations of that form. So here's our one example of something we can do with differential equations. And in this case, we're given a y equals sine of x cosine of x minus cosine of x. And we're supposed to verify that that is in fact a solution to the initial value problem, which has a differential equation and an initial condition on an interval negative pi over 2 to pi over 2, which I think that is there as a domain restriction so that we don't run into issues with tangent of x, right? Because it's not defined outside or has some asymptotes at those points. So that restriction there is mainly just to make sure that we have a tangent we can take the derivative of. So all we have to do is verify that this is a solution. And so what we're going to need to do is we're going to plug y in everywhere there's a y, which is right here. And then we're also going to need y prime so we can plug it in. So the first thing we'll do is find y prime. And y prime, it looks like we're going to need the product rule as we take the derivative of sine of x times cosine of x. So we're going to have sine of x times a negative sine of x, and then plus cosine of x times cosine of x, and then minus a negative sine of x if we take the derivative of cosine of x for that last part. So we had a product rule first, and then a regular derivative of sine. And if we multiply this out, it looks like at negative sine squared of x plus cosine squared plus sine of x. So that'll be our derivative. So we know our derivative, we know we have tangent x, and we have a y, and our goal is to show that it's equal to cosine squared of x. So we're going to start with one side of the equation, and we're going to get the other side. And our goal is to get that other side. So we have, in our situation, y prime plus tan of x times y. So if we start plugging this stuff in, we get negative sine squared of x plus cosine squared x plus sine of x, and then we're going to take plus tangent of x times y, and y was sine of x cosine of x minus cosine of x. So now it's just a major algebraic simplification. Our goal is to get that it's equal to cosine squared. So it looks like we're going to need a few more steps here for sure. So let's see. This first part, we don't have any simplification to do there. Negative sine squared plus cosine squared plus sine of x. And then I think one way to think about this is to keep in mind that tangent is sine of x over cosine of x. And if we use that and start distributing it through to these two terms here, it looks like we'll get plus sine squared x cosine of x over cosine of x, and then minus cosine of x sine of x over cosine of x. So if we have all of that, you'll see that some stuff will cancel. These cosines will cancel, and then we'll have, I believe, these sine squareds will cancel here. And then also plus sine of x, and this ends up being minus sine of x, all cancels. So it looks like everything cancels except cosine squared, which is exactly what we were hoping for. So this is in fact equal to cosine squared of x, and we have verified this first part of the differential equation. So when I ask you to verify, you're really just finding your derivatives, any derivatives that it asks you to find, and then you're just plugging those into the equation on that one side and just making sure that you get what's on the other side. Now we just need to check the initial condition to make sure that that also is satisfied. So if we do that, it looks like we need to check that y of 0 is equal to negative 1. And so in this case, if we check out y is, remember, sine of x cosine of x minus cosine of x. And so we just plug in 0, and we should get negative 1. So y of 0 is sine of 0 times cosine of 0 minus cosine of 0. And so that's 0 times 1 minus 1, which is negative 1, and that is in fact a good deal. So we have in fact verified both things that it asked us to check. The initial condition, that's this part here, we got that, and on the last page we checked that the equation was correct. And it literally is just plug it into one side and make sure you get what's supposed to be there. That's all you have to do on a verify. So you actually know where you're going. You just have to do the algebra and simplification in order to get there.